The next application for the op-amp is called the difference amplifier circuit, and this is one of the important applications of the op-amp. The difference amplifier, basically, it's an amplifier that should maximize the difference between two sources. So if you have two sources, whatever you call them, you can call them V input 2 and V input 1. The difference amplifier is supposed to amplify the difference between V input 2 minus V input 1, which we call V differential. V differential, or sometimes they call it V differential mode, okay? VDM. So VDM is the difference between the two sources. The first source is the one connected to the non-inverting input of the op-amp, and the second source here is the source connected to the inverting input of the op-amp. However, they found that unfortunately the difference amplifiers that we design in practice, usually they do not amplify only the difference between the two sources, they also amplify the average value between the two sources, which is V input 2 plus V input 1 over 2, which we call V common mode. So they found that we want to amplify the difference, but they found that practically speaking, the difference amplifier doesn't only amplify the difference, it amplifies also the average, which we call V common mode. So this is called common mode voltage, and this is called differential mode voltage. The target or the goal is to maximize the differential mode voltage, the difference between the two sources. However, the difference amplifier amplifies not only the difference, it amplifies also the common mode voltage. So the output of the amplifier, usually it looks like this. The output of the amplifier, it's the differential mode voltage multiplied by a certain gain, which we call the differential mode gain, plus the common mode voltage. It will be amplified by a gain called the common mode gain. Of course, as I said, the main goal was to amplify only the differential mode voltage without amplifying the common mode voltage. But here it amplifies the common mode voltage, which represents here, this term represents a disadvantage for us, right? So the amplifying the common mode voltage is bad here. So they measure here, they define the measure for the efficacy or the how good this difference amplifier is. When they compare the two difference amplifiers, they defined a measure to say which one is better than the other. They defined the measure called the common mode rejection ratio. The common mode rejection ratio, from its name, common mode rejection. How much you reject the common mode, how much you reject this term. Because as I said, the main goal was to maximize only the differential mode, the difference between the two sources. So they measure the efficacy or how good this difference amplifier by measuring how much it rejects this term, common mode rejection ratio. They measure it, or they define this common mode rejection ratio as the ratio between the differential mode gain, the gain that the difference amplifier amplifies the differential mode voltage with, divided by the common mode gain, which is the gain that the difference amplifier amplifies the common mode with. And then they convert it to dB by taking 20 log. So the common mode rejection ratio tells you how good your amplifier is, how good your difference amplifier is. If the differential gain is much higher than the common mode gain, the common mode rejection ratio will be high, which means that your difference amplifier is good. But if the differential gain is close to the common mode gain or less than the common mode gain, the common mode rejection ratio will be very low, which means that your difference amplifier is bad. So the common mode rejection ratio, as it increases, this will be better. The higher the common mode rejection ratio, the better the difference amplifier. Okay? So the common mode rejection ratio, it's a measure of how good your amplifier is. It is 20 log the ratio between the differential mode gain, this term, divided by the common mode gain, this term. Okay? So that was an introduction for the difference amplifier. Practical difference amplifier, again to conclude, it doesn't amplify only the difference, but it amplifies also the average level between the two sources. Okay? This will be amplified by a gain called differential mode gain. This will be amplified by a gain called common mode gain. And then the ratio between the differential mode gain and the common mode gain indicates how good your difference amplifier is. And we call it the common mode rejection ratio. The highest, the better. Okay? Right. In order to analyze a difference amplifier circuit, we need to represent the two sources, our two sources V input 1, V input 2, in terms of the difference and the common mode, in terms of the difference voltage and the common mode voltage. So what they do is they represent the two sources as following. They say that V input 2 can be written as V common mode plus V differential mode divided by 2. And they define V input 1 as V common mode minus V differential mode over 2. Let's make sure that this is correct. If we take V common mode and we add it to V differential mode over 2, V common mode and we add it to V differential mode over 2, what we will get? V common mode is V input 2 plus V input 1 over 2 plus V differential mode over 2. It will be V input 2 minus V input 1 divided by 2. Of course, we'll see that V input 1 over 2 will cancel with minus V input 1 over 2, and this will give you V input 2. So we can write V input 2, the source connected to the non-inverting terminal, connected to the non-inverting terminal can be written as V common mode plus V differential mode over 2. The other source also similarly can be written as V common mode minus V differential mode over 2. Let's make sure. V common mode is V input 2 plus V input 1 divided by 2 minus V differential mode over 2, which is V input 2 minus V input 1 over 2. Here you will find that V input 2 over 2 will cancel with V input 2 over 2, and V input 1 over 2 will be added to V input 1 over 2, so this will give you V input 1, which is correct. So we can write the source connected towards the inverting terminal as V common mode minus V differential mode over 2. And hence we can, if you have two sources, this source will be connected to the non-inverting terminal and this source will be connected to the inverting terminal. You can represent them as the following figure. V common mode, source with a value V common mode, and then another source here in the same direction, V differential mode over 2. So now this is the direction of V common mode, and this is the direction of V differential mode over 2. The voltage here will be V common mode plus V differential mode over 2, which is VI2. And here we put V differential mode over 2 reversed. So the voltage here at this point will be V common mode minus V differential mode over 2, which will give you V input 1. So any two sources, they can be represented as V common mode, this is the average between the two sources, plus and minus V differential mode over 2. Yeah, this point is just will be used for mathematical analysis of the difference amplifier, as we'll see. Let's now go to see the general form of the difference amplifier. The general circuit for the difference amplifier, it looks like this. We have two sources. Here, V input 2, we'll call it VB for simplicity, and V input 1, we'll call it VA. VB is connected towards the non-inverting terminal of the op-amp. VA, which was V input 1, will be connected to the inverting terminal. This is the circuit of the difference amplifier. This circuit can be analyzed in many ways. many ways. You can use all the tools that you learned in the circuit analysis to analyze this circuit. One of them is to do superposition. Let's do superposition. If we do superposition, we can first say that short circuit VA, assume that you have only VB in the circuit, and this is short circuit here. In this case, this will be very similar to the circuit that we solved in the previous video, the circuit of the non-inverting amplifier that we solved in the previous video. First, there will be a voltage divider here, VB multiplied by RD over the sum. This will give you this voltage. So let's take, we'll do superposition. And I want you to solve this circuit by yourself. After you watch the video, go back and try to solve it by yourself to just make sure that you can analyze the op-amp circuit. So we'll consider only the source VB, so the circuit will look like this. This is ground because we will short circuit VA, so this will be ground. This is a resistance called RA, resistance called RB. This is V output dash. V output dash is the component of V output that will result from source VB only. Okay, so this is superposition. You have to review the superposition. Okay, and this is VB. Similar to the previous example, or the example that we solved in the previous video, there is no current here. The current here is 0. So we can use voltage divider. We can calculate the voltage VP. The voltage VP across the resistor here will be VP equals VB multiplied by RD over RC plus RD. And this voltage VP is the same as Vn, right? So Vn is the same. And then Vn will be amplified using the same rule of the non-inverting amplifier. It will be multiplied by RB plus RA over RA to get the V output dash. So V output dash here will be Vn multiplied by 1 plus RB over RA, which will be VB multiplied by RD RA plus RB divided over RA multiplied by RC plus RD. So this is the output that will result, V output dash, that will result only from the source VB. Right, let's consider the other source. Superposition, you have to consider the first source and then the next source. The second source, the circuit will look like this. This is V output double dash. Okay, this is negative, this is positive. Okay, and then here the source VA will appear here. And VB will be short-circuited. Why? Because again we are doing superposition, right? So this is a resistance RC and this is a resistance RD. Of course here, if you look carefully, you find that this part has no current at all, because there is no current here, there is no source to generate any current, and there is no current from the op-amp. So the current in these two resistors will be 0. So basically these two resistors are useless here in this analysis, right? So the voltage here, VP, will be 0 and the voltage Vn will be 0, and the circuit will be very similar to the inverting amplifier because there is no current in this part. In this part, we don't have any current, no current. So we can say, since this is very similar to connecting this directly to the ground, okay, this will be very similar to the inverting amplifier circuit, and the output, V output double dash, will be equal to VA multiplied by minus R, the feedback resistor here, we call it RB, and this is RA, minus RB over RA. Now we calculated V output dash and V output double dash. V output total is the summation of these two terms. So V output total will be the summation of V output dash plus V output double dash, which is already negative. This is V output now of this difference amplifier in terms of VB and VA. As you see, in general, V output is not amplification of the difference, because VB is multiplied by something and VA is multiplied by something else, completely different. So the output here is not an amplification of the difference. How can we analyze? We'll go back to the definition of VB and VA in terms of the common mode and the differential mode segment. We already defined VB. We already defined VB to be V common mode plus V differential mode over 2, and VA to be V common mode minus V differential mode over 2. If we take these expressions and we replace VB from here with V common mode plus V differential mode over 2, we replace VA here by V common mode minus V differential mode over 2. In this case, we'll get an equation in V common mode and V differential mode. This is multiplied by something and this is multiplied by something. And I need you to try it at home. Try to just replace VB by this expression and VA by this expression. You will get an equation that is V common mode multiplied by some resistors and V differential mode multiplied by some resistors. And this expression will look like this. This is the expression. It will be the common mode gain, which is given by this expression, multiplied by V common mode, plus the differential mode gain, which is given by this big expression, multiplied by V differential mode. So as you see here, the output of the difference amplifier in general, it's not only the amplification of the difference. You amplify also the common mode voltage, which is bad. This is something that we don't want it to happen, right? So we need somehow to cancel this term. So the only way to cancel this term is to make the common mode gain to be 0, right? So if we can make the common mode gain 0, then this term will cancel and this difference amplifier will be perfect, right? So the way, or the only way to cancel the common mode gain is to make the numerator equal to 0. In order for the common mode gain to be 0, you need RA, RD to be equal to RB, RC, which in other words, you can write it as RB over RA equals to RD over RC. So this is the condition for the common mode gain to be 0. Basically, remember it, don't remember the equation, because the equation is tricky. If I give you some other symbols, or I give you the resistors flipped, RA is there and RB is here and RC. So if I change the naming of the resistors, you will be confused. So remember as following: this over this must be equal to this over this. The resistor here up over the other resistor up right over up left must be equal to down right over down left. RB over RA must be equal to RD over RC. Up right over up left must be equal to down right over down left. Okay, this is the condition for the common mode gain to be 0. Sometimes one option to choose these resistors is to choose RB to be equal to RD and RA to be equal to RC. So usually they use RA equals to RC, this resistor is equal to this resistor, and RB is equal to RD. This will satisfy the relation, and in this case, the output will be equal to the common mode gain, which is 0 now, multiplied by the common mode voltage, plus RB over RA. In this case, the differential mode voltage, if you substitute this relation here, you will find that the differential mode voltage will be RB over RA. So in the case here that the common mode gain equals 0, in this case the differential mode gain will be the ratio RB over RA. So this is something that you need to memorize. The condition for the common mode gain to be 0, and what happens in this case for the differential mode gain. So the condition again is this resistor over this resistor equals to this over this. In this case, the common mode gain will be 0, and the differential mode gain will be this over this, RB over RA. And you can verify it from here. Try to consider this ratio satisfied and substitute here RB over RA. For example, take RA as a common factor, take RC as a common factor. You'll find that here you have the same bracket exactly. Okay, and then work out this expression. You'll find that the differential mode gain will turn out to be RB over RA. You can do it at home, okay? And maybe I'll ask you to do it in class. So this is, for now, this is some information about the difference amplifier, how we measure the efficacy of the difference amplifier, how we make the common mode gain be 0, and what happens to the differential mode gain in case the common mode gain is 0. We'll stop here in this video, and next video we'll discuss some other issues about the difference amplifier.